Hello class, and thank you for watching. In this video, you will learn how to transform functions and identify the vertex of an absolute value function. A transformation changes the size, shape, position, or an orientation of a graph. Today, we're going to focus on the parent function, or on the function, better said, the absolute value function, and how we transform this function using vertical shifts, horizontal shifts, vertical dilations, and a reflection, and how that affects the graph. Let's start with vertical shifts. If you look at the original parent function has a vertex. Let's start with that. Has the vertex at 0, 0. And the domain is from negative to positive infinity. The range right now at its parent position is all of the y values from 0 to positive infinity. Because again, as you clearly see, this graph exists no lower than this blue line and only exists above the v. Again is pointing upwards, and it can only be found above this line, which is at y is equal to 0 all the way to positive infinity. Well, what happens again when we transform this and we affect the graph by shifting it up or down? Notice how this graph has been shifted up from this position of 0, 0 up to this point right there. It shifts up exactly 2 units because we're adding 2 to the absolute value of x. As you see right here, there's the absolute value. That's what makes the v, and we're adding 2 to it. So instead of it going down and starting at the origin, the vertex being at the origin, the vertex has now been shifted up 2 units. Now, if the graph is shifted down 2 units, again, here's the original parent function where the vertex is at 0, 0. If it's shifted down 2 units, that's the result of subtracting 2. So the way we describe these two transformations, on the left, we say that the absolute value function is shifted 2 units down. And over here, our absolute value function, up. This one right here is up. Up. And this one over here on the right is down. So in general, the general transformation of this, if we're adding a value, a k, we'll call it k. If we're adding some value of k to our function, whether it's this function or anything else, it's going to result in a vertical shift. So if we're adding 2, it shifts up 2. We're subtracting 2, it shifts down 2. So for vertical translation, f of x plus k means the following. It means that our function f of x, whatever it is shifted k units up because we're adding it. And when we subtract it, it shifted k units down as a result. Now, let's go to the next page of our notes and let's discuss horizontal transformations. Now, you'll notice that for horizontal transformations, to shift it left and right, we're not adding, the adding or subtracting is not on the outside. It's actually included within the absolute value symbol within this 2, again, vertical lines, the absolute value symbol. And pay attention to what's happening here. Now, if I have x and I subtract 2 inside the absolute value symbol, it doesn't shift it down, but instead it shifts it to the positive direction by those 2 units. Now look at the example on the right. If I add those 2 units, again, still inside the absolute value, instead of shifting it up, it shifts it to the left 2 units. So the direction for a horizontal transformation is going to be an addition or subtraction inside the absolute value, again, specifically to the x coordinate, in the opposite direction. Subtracting moves it in a positive direction, and adding moves it in a negative direction. So here the description for this shift would be that, again, our absolute value function is shifted two units to the right, and over here our absolute value is shifted 2 units to the left. Okay. Now, a horizontal translation for a general, just in general, is shifted to the graph either left or right. And the notation for that would be this. This is the wrong notation, so let's scratch that out. And the right notation would be f of x plus, we'll use the letter h instead of k, h for horizontal. So if we add that h to this x, this is going to be a shift of h units to the left. If it's adding, it's to the left. And if it's f of x minus h, again, we're subtracting the h to this x, then this is going to result in a shift of h units in the opposite direction, and to the positive side, to the right. So for horizontal shifts, it has an opposite effect. Adding moves it in the negative direction, subtraction moves it in the positive direction. So let's see if we have this. So pause the video and determine what these numbers are going to do to the function. And then when you're done, unpause it and check your answers. So let's check your answers. Check your answers here. Okay, so here for the first one, this plus 12, because it's on the outside, is going to result in a vertical shift. And because of the adding, it's going to be up. So this is going to shift 12 units up. Now the one on the bottom, because the 6 is being added on the inside, is going to result in a horizontal shift. And 6 is going to move it in the opposite direction. So this is going to result in a shift of 6 units in the negative direction. So that's going to be to the left. And now let's look at the minus. Well, the minus on the outside, subtracting the absolute value of x by 7, this is going to shift this thing 7 units down. But subtracting on the inside is going to result in a horizontal shift of 3 units, but in the positive direction, which is going to be to the right, the opposite. Opposite of subtracting 3 would be adding 3, so you shift the 3 units to the right. Now let's discuss vertical dilations. So for vertical dilation, we could do one of two things. We can make it closer. Again, this, let me highlight the parent function. This is the parent function f of x. And this is the transformation g of x. Okay, that's this one right here. If we make the graph closer and push it in closer to the x-axis, we are stretching it vertically. We're pulling the graph up. So the closer it is to the y-axis, the more stretched it becomes. So this results in a stretch. In a stretch by 2. 2 because that's what we're multiplying by. So this type of transformation is the result of not adding or subtracting, but instead multiplying a number in front of this absolute value symbol. So in front of these symbols right there, okay? And if this number, in this situation 2, it's making it closer to the x-axis, again, which means it's being stretched vertically by 2. Now, if I make the function farther away, so look, let me again highlight the original function in yellow. So this is the parent function, and I multiply this parent function by 1/2, like I'm doing right here in H, that's going to result in this wider graph. So this graph that's being pulled away, making it farther away from the x-axis, which vertically, that implies, that means is that you're stretching it, or I'm sorry, shrinking it downwards. You're making these points lower than they normally are. So this is referred to as a shrink by, in this situation, by 1/2, because that's what we're multiplying by. Okay? So we end up with a stretch or a shrink by what we multiply, what we're multiplying by. And if you use, again, your number sense, your ability to multiply numbers, it will make sense that a stretch is a result of multiplying by 2, a number greater than 1, and a shrink is a result of multiplying by a number less than 1. So the bigger the number, the more it stretches. The smaller the number you're using, the more it shrinks. So a vertical dilation multiplies values by a number to either stretch or shrink the graph vertically. So if we're multiplying by a value of a, and that value of a is a number greater than 1, then that's going to result in a stretch by a factor. That's the terminology that we say that we're multiplying a by a factor of a. And if we multiply by a value of a, we say that we're going to, again, by a factor of a, and that value of a is a number less than 1. So again, that's what this one's saying right here. When a is less than 1, then we're going to end up with a shrink. So we're going to shrink the graph by a factor of a. And then lastly, we have a reflection. A reflection is a transformation that flips the graph over a line called the line of reflection. We usually refer to this line as the x-axis. So right here, if we multiply by a negative, okay, ignore if it's negative, a -3, -4, just as long as it's negative. We don't care about what type of negative it is. As long as there's a negative right there, when we're multiplying by a negative, this is going to result in a reflection. And the way we describe it is that we say we flip it upside down, or we just simply reflect over the x-axis. The -2, -3, or -1/2, that has no the determining factor that it flips. The fact that it has a negative determines that it flips. The number itself, this number of a, the a will result in a shrink or a stretch by that factor. That it has a negative in it does not affect, again, or it doesn't affect whether it's going to be flipped. Okay, the negative sign does, not the a itself. Okay, so let's look at some examples of this. So let's move on to the next page. Okay, so for this example right here, let's describe the transformation for the function when compared to the parent function. So here, well, notice that we're subtracting 5, but on the inside. So that's going to result in a shift of 5. So we're going to shift by 5 units. And in this situation, it's going to be to the positive side to the right. Now, in the next example, we have 2 transformations. We have this +9 on the outside and this 1/2. Let's start with the +9. Because of the +9, that's going to result in a shift of 9 units. Now, the direction that the 9 is going to move it is going to move it up, because we're adding 9 to the outside. If it was the 9 on the inside, like if it was like this, then that will result in a shift of 9 units, but to the left and not up. But with the 9 on the outside, that results in an up. Now, What is the 1/4 going to do? Well, the 1/4, because we're multiplying, that's going to result in a dilation. And specifically, it's going to result in a shrink because 1/4 is less than 1. It's a number that's smaller than the 1. And anytime we multiply by a number smaller than 1, that's going to shrink the graph. So this is going to result in a shrink. So those are the transformations. We have a shift of 9 units up and a shrink by 1/4, by a factor of 1/4. Now for number 7, we have two transformations yet again. We have this 4/3. We're multiplying by 4/3, and we're adding 6. Well, since the adding of 6 is on the inside of the absolute value, that's going to be a horizontal shift in the opposite direction. So positive 6 shifts it in a negative direction, so to the left. So we're going to shift this graph 6 units to the left. And now let's discuss what the 4/3 does. Well, since the 4/3 is a number greater than 1 and we're multiplying by that number greater than 1, then this is going to result in a stretch. In a stretch by that scale factor of 4/3. And now finally the last example number 8. We have three transformations here. We have the negative sign, we have this +7 on the inside, and this -2 on the outside. Well, let's start from left to right. The negative sign, that's an automatic reflection. Multiplying by a negative, whether it's a number greater than 1 or less than 1, doesn't matter. It's going to be a reflection, okay? Now, since that number is just still 1, there is no dilation. It doesn't get stretched or shrink because we're not multiplying by a number greater than 1 or less than 1. We're multiplying by 1, so it does not change. Now, the +7 on the inside, well, that's going to result in a horizontal shift of 7 units. So we're going to shift 7 units in the opposite direction, so to the negative side, which is the left. And the -2, because it's on the outside, is a vertical shift. So this is going to result of shifting 2 units in a negative direction, so 2 units down. And that's the transformation for this example. Now, finally, to graph an absolute value function, we need two things. We need to figure out the vertex and the transformations. So the vertex form of the absolute value function is the result of this scalar a times the absolute value of x minus h, which is the horizontal shift. So this is your horizontal shift, plus k, which is your vertical shift. And this a is your dilation. So the horizontal and vertical shift describes the location of this vertex. And your vertex, h, sorry, let me do it in color, this color, h, comma, k, is your vertex. So as an x and y value, h and k, whatever these numbers are, will describe again the location of your vertex, the shift of the graph. And a is the slope on the right side. This value of a, this number right there, a, is the slope on the right side, and negative a is the slope on the left side of this center point, aka the vertex. So let's see, let's identify what the vertex is in this vertex form, okay? So to identify the vertex of example number 9, we're going to first look at the shift. Well, the -2, because it's on the inside of the absolute value, is going to shift it in the opposite direction. So it's going to shift it in a positive direction of 2. So the vertex is going to be at +2 for x. Now, the minus 4 on the outside is going to result in a vertical shift of 4 units down. So we're going to go down to negative 4. So our vertex is at positive 2, negative 4. So it has been moved from here. So this graph, again, the parent function that normally looks like this, has been shifted 2 to the right and 4 down to this location there. Now, since the value of a, this number right here, is 1, that's going to be the slope moving to the left and to the right. So from this point here, the vertex, from the vertex, we're going to move up 1 over 1, up 1 over 1. And the v on the right side is going to look like this. Now, because the v is symmetrical, the left side is going to look exactly as a reflection. So we're going to move up 1 now to the left. Up 1 to the left, up 1 to the left. And this is what the graph is going to look like. But again, it starts by first identifying our vertex, plotting that point as the center of our v, and then simply drawing the v by following the a value as our slope. So let's look at another example. Let's look at this example where a here, the a value is 3. And let's look at our vertex, our shift. Well, since the 3 is on the inside, that's going to be a horizontal shift in the opposite direction. So plus 3 means left 3. So that's going to be negative 5. And because we're not adding anything on the outside, it's technically plus 0. So there is no vertical shift. So our vertex is going to be simply moved to the left 5 units and not up or down. So that's going to stay right there. So again, normally remember, the parent function normally looks like this. And this center point is right here at 0, 0 normally. But because of this plus 5, that is going to shift it to this new location there. Now let's see how the V is going to look, how wide the V is. Well, the width of the V depends on this value of A. Since this value of A is 3, that means that from this vertex, we're going to move up 3 units, 1, 2, 3, over 1. 1, 2, 3, over 1, and 1, 2, 3, over 1. So the right side of the V is going to look like this. And because, again, a V is symmetrical, the left side is going to simply match up to it, just moving in the opposite direction. So from the vertex, if I count 3 units up and move to the left, I'm going to be at this point there. Count 3 units up and 1 to the left, that's going to be that point there. And if I connect those, this is the sketch of that absolute value. So the V will look like that. Okay, so now let's look at the next example. In this next example, let's identify first the vertex, and then we'll go to the next page and graph it. So let's see, we have 2 over 3, x plus 1 minus 1. You know what, let me just write it over here, so we're not going back and forth. So f of x equals 2 over 3 times the absolute value of x plus 1, close the absolute value, minus 1. Let me just double check. Yeah, plus 1 minus 1. Okay. So let's start first again with the vertex. Well, our vertex is the result of our horizontal and vertical shift. Well, the minus 1 moves it horizontally in the opposite direction, the one that's inside. So the plus 1, the plus 1. So that's going to move it 1 unit to the left. So that's going to be at negative 1. The minus 1 on the outside is a vertical shift of 1 unit down, so negative 1. So our vertex has been shifted 1 unit to the left and 1 unit down. So this is where the center is. Now the value of A is this number here. A equals to 2 over 3. Well, we can't go up 2/3 of a unit and 1 over. So what we do instead, because this is a fraction now, we use the top number as the rise and the bottom number as a run. And remember, we're drawing a V, so this is going to look symmetrical. So we're going to go up 2 units from the center. We're going to go up 2 units, 1, 2, and then 3 units to the right, 1, 2, 3, and 3 units to the left, 1, 2, 3. Again, from the center. So this again is the center of the V. So we need to make the V look like that. And if we need more points to make it better, make it a little bit straighter, we can. So we continue going up 2, and then 1, 2, 3, up 2, and then 1, 2, 3. So the right side of the V will look like this. And the left, I just continue counting up 2 and over 3, but just going in the left direction. So up 2, so 1, 2, and then 1, 2, 3, and then up 2, and then 1, 2, 3. So the graph looks like that. Okay. Now, for the next example, let's see, for this last example here, again, to graph this one, let me remind myself what the function was. Negative 3 over 4x plus 7. Negative 3 over 4 times the absolute value of x plus 7. Let's start with the vertex. Well, our vertex, again, has no horizontal shift. Notice that inside this absolute value, we're adding anything to the x. So no horizontal shift means it's going to stay at the center at 0. But the plus 7 is going to move it up 7. So our vertex is going to be located at 0, 7. So that's where the center of the V is going to be. Now we have A is 3 over 4. There is a negative sign there, but what the negative sign does is that it flips it. It reflects it across and flips it upside down. So instead of going up 3, our rise is going to be negative and is going to go down 3. And the 4 is going to be like the run to the left and run to the right. So here, to draw this graph, the 3 will, from the center, will move down 3, 1, 2, 3, and then 4 to the left. I'm sorry, 4 to the right first. 1, 2, 3, 4. And then 1, 2, 3, and then 1, 2, 3, 4 to the left. And when we connect those points to the center, that's what our V is going to look like. Now, we don't need more points. If you want to draw more points, you're more than welcome to draw more points to make the line straighter, but with those is enough to make the V. I'm going to do it, okay? So from this point, I'm going to count 1, 2, 3 because of this number there, and go down because of the negative sign. 1, 2, 3, and then 4 to the left. 1, 2, 3, 4. So I have the left side of the V. Now to draw the right side, I just follow the pattern in the direction for right. So 1, 2, 3, 1, 2, 3, 4. And look again at the symmetry of this. So there. That's what this graph will look like. All right, your assignment again is posted on Edgelastic. If you have any questions, please send me a message through email. Send me an email. And I appreciate you watching, and I hope you have a great day. Goodbye.